Okay, in the last lecture we are discussing about the data flow modeling. So, we have discussed about the data flow modeling of some combinational circuit such as multiplexer, decoder, then half adder, full adder, ripple carry adder. So, the next adder is carry look ahead adder. CLA. So, because the drawback of the ripple carry adder is, so the carry will propagate through the stages. As a result of that, the total propagation delay depends upon the number of stages. Okay. In general, if you want to add two n bit numbers, then the total propagation delay is n times that of the full adder. Okay. So, that is the drawback of this ripple carry adder. To avoid that, we can use this carry look ahead adder, where regardless of the number of stages, the delay caused for the performing the addition will be same. Okay. So, what is the idea behind this carry look ahead adder? So, if I take any ith stage and I plus 1 stage, this is typically a full adder, and we are considering this as a ith stage, AI, BI, CI, and output will be CI plus 1. And this output is SI. This is a typical ith stage. You can see from this the previous this one also. So, here you can see here for the 0th stage, these are 0, A0, B0, output is S0, input is C0, output is C1. For the first stage, these are 1, 1, 1, 1, and this is 2. So, like that, if I take the ith stage, this is CI, AI, BI, SI, CI plus 1. Now, here as the name implies, we are going to generate all the carriers at a time. Okay, instead of generating this C1 first and then C2 and then C3 and so on, we will generate all the carries simultaneously. Okay. So, in order to generate these carries simultaneously, so what is the logic that we have to follow? Okay. If I consider this ith stage only, so when does this Ci plus 1 becomes 1? So, what are the conditions for this? This is basically adding 3 numbers, AI plus BI plus CI. So, this will give 2 bits sum and carry, this will give CI plus 1 SI, this is sum bit and this is carry bit. So, we are not interested in the sum bit, okay, let us forget about this. So, when does this carry bit will be 1, this Ci plus 1. So, what are the conditions? For the carry bit should be 1. So, Ci plus 1 is equal to 1 if any 2 bits are 1. So, among these 3, at least 2 bits has to be 1. Okay. So, among all the 8 combinations, what are the combinations? So, this is AI, BI, CI. If I take all the combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Among all these combinations, so what is this sum Ci plus 1, when does this will be 1? So, 0 plus 0 plus 0 is 0, there is no carry, 0 plus 0 plus 1 is 1, sum bit is 1, carry is 0. This is also sum bit is 1, carry bit is 0. Here you will get carry bit 1 as sum bit is of course 0. Okay. If you want to write this sum also, we are not interested here, but I will write this. This is 0, this is 1, this is 1, this is 0. And here also, because only one input is 1, carry is 0, but sum is 1. Here two inputs are 1, so carry is 1, sum is 0. Here also carry is 1, sum is 0, here both will be 1s. This is the truth table of a full adder, right. So, the condition for Ci plus 1 to be 1 is, so here at least two inputs has to be 1. This is 1, this is the combination where this output Ci plus 1 is 1, this is another combination, this is another combination. Okay. So, out of these 8 combinations, in 4 combinations Ci plus 1 is equal to 1. Okay. So, how do you represent this using a Boolean expression? Okay. So, in order to represent this using the Boolean expression, Ci plus 1 is equal to, we can derive in terms of A, B, C, okay, but I am going to derive in terms of exclusive OR and AND operation, so that I can define some terms like carry propagate and carry generate. Okay. So, one condition is if A and B, if I assume that both A and B's are 1, I can write this Ai, Bi. So, if both are 1s, then only Ci plus 1 is 1. If any one of this input is 0, Ci plus 1 is 0. If I write only this condition Ai, Bi, so this will cover these two combinations. These two combinations will be covered by simply Ai, Bi, because in these two combinations both Ai, Bi are 1. Okay. But there are two more combinations in which Ai, Bi are not 1, still Ci plus 1 is 1. So, how to cover these two? If I write simply Ci plus 1 is equal to Ai, Bi, it will cover only these two combinations, but I have to cover these two combinations also. So, for that I have to add some more extra term plus. So, what are these two combinations in which A is not equal to Bi? Okay. So, A is not equal to Bi, still Ci is equal to 1. Okay. This can be represented by Ci Ai exclusive OR with Bi. So, in these two combinations Ai is not equal to Bi, so Ai exclusive OR with this one. So, one of this one is 0, so this will be 1, this operation is 1, and if Ci is equal to 1, then this product term is equal to 1. If Ci is also 1, this product term is 1, thereby the Ci plus 1 is equal to 1. So, what are the two conditions under which this Ci plus 1 is generated is, if A, Bi both are 1s, then is one condition, or if A is not equal to Bi and Ci is equal to 1. So, if you want to write in the words statements, we can write Ci plus 1 is equal to 1 if Ai is equal to Bi is equal to 1, or Ai is not equal to Bi and Ci is equal to 1. Okay. So, this statement can be mapped onto the Boolean expression using this. A is equal to Bi is equal to 1 is A Bi, A is not equal to Bi is A exclusive OR Bi, Ci is equal to 1 into Ci, and this AND is there, this is AND operation here, this is OR is there, this OR operation. So, this expression for this Ci plus 1 is equal to Ai Bi plus Ci times Ai exclusive OR Bi. So, I am going to define this as Gi as A AND with Bi plus Ci Pi, where Gi is AIBI is called as carry generate. So, this will generate the carry, and PI is AI exclusive or BI, this is called carry propagate. So, this is carry generate and this is carry propagate, because this is going to propagate the carry of this Ci. Okay. So, in terms of Gi and Pi, Ci plus 1 is Gi plus this. So, I can generate the Ci plus 1 from Ai, Bi, Ci. Then what about Si? So, for a fully adder, what is the expression for the sum? Si is nothing but exclusive OR of all the 3 inputs, Ai exclusive OR, Bi exclusive OR, Ci. But Ai exclusive OR Bi we are calling as propagate signal. So, you can simply call this one as Pi exclusive OR with Ci. So, in order to design this carry look ahead adder, the very first step is you have to generate all the generate signals and propagate signals. Given A's and B's and C's, first you have to generate G's and P's. Okay. So, after that you have to find out all the carries, then after that we will find out the sum. So, there are 3 steps in the carry look ahead adder. The first step is you have to produce all the generate signals and propagate signals, okay, using some logic. Then the second step is using this generate and propagate signals, you have to generate all the carries simultaneously. The third step is using these carries and the Ci, we have to generate all the sums. Okay. So, we will discuss now how to generate this all the carries simultaneously. So, if I consider this 4-bit look ahead carry adder CLA. So, the input is first 4-bit number A3, A2, A1, A0, B3, B2, B1, B0, and also will be given the input carry also C0. These are all available. So, very first step is here you have to generate all the propagate and generate signals. So, what is G0? In general Gi is Ai Bi. Ai Bi is Gi and Ai exclusive OR Bi is Pi. So, G0 is A0 B0, G1 is A1 B1, G2 is A2 B2, G3 is A3 B3, and then propagate signal Pi is equal to Ai exclusive OR Bi. So, what is P0? Is A0 exclusive OR with B0, P1 is equal to A1 exclusive OR with B1, P2 A2 exclusive OR with B2, P3 A3 exclusive OR with B3. The first step is compute carry generate and propagate signals. This is your step 1. So, regardless of the number of bits, we have only 3 steps, unlike ripple carry adder. In case of CLA, we have only 3 steps only. The first step is we will generate all the generate signals and propagate signals. If it is 5-bit, you will generate G4 and P4 also. If it is 6-bit, you will generate G5, P5 and also. Okay. So, for this what is the circuitry? We require a AND gate, all these will be generated simultaneously because these are all available. Okay. So, this all G signal can be generated using AND gate, this will be generated by exclusive OR gate. Of course, the delay of exclusive OR gate is more than that of AND gate. So, what is the computation time to perform this step 1? The computation time for this one is T XOR gate, because parallelly all will be generated. So, this is A0, B0, because these are all available, this will generate G0. Similarly, we have G3 using A3, B3, A0, B0 will get P0, so on up to A3, B3 will get P3. So, all this will be generated parallelly, but because this delay time is more, okay, after this time of T exclusive OR gate, so all G's and P's will be available. Of course, these G's will be available before the P's are available. Okay. So, if I wait up to T XOR, because without generating the P's I cannot generate the all carries. Okay. We are going to follow the second step. In the second step we are going to use all G's and P's. Okay. Even though you generate these G's a little bit faster than these P's, so you have to wait until these P's are generated. So, after a time of T XOR seconds, all the P's and G's will be generated. Now, we will proceed for the second step, generate all the carries. Now, what are the inputs for this carry generator? We have G's and P's, even we have C0 also. Okay. So, what is the expression for Ci plus 1 is equal to Ci plus Pi Ci. So, C0 is the input which is given here available. So, I find out C1 first. How to generate C1? So, I is 0. So, C0 plus P0, this is Gi plus Pi Ci, G0 plus P0, C0. Okay. So, this G0, P0 are generated in the first step and C0 is already available along with the A's and B's. So, I can generate this C1 after some time. What is the time taken to generate this C1 is when AND operation, one OR operation. Okay. Now, C2 is given by G1 plus P1 C1. If I compute this C2 using this expression, then this C1, so after generating this C1 only I can compute the C2, but here in this step I want to generate all the carries simultaneously. For that you have to substitute this C1 here, G1 plus P1, what is C1? G0 plus P0 C0. So, that we know this P1, G1, G0, P0 which are generated in the first step and C0 is available at the starting of the this design. Okay. So, we can generate C2 after a time of this logic gates. Okay. So, C2 will be generated after a time of the time taken to perform this all Boolean operations. Then C3 is G2 plus P2 C2, this is equal to G2 plus P2 into C2 is nothing but we have to substitute this P2 G1 plus P1 into G0 plus P0 C0. Again further simplify this expression so that we will get the simplified circuit. So, So, this is equal to G1 P1 G naught G1 plus P1 G naught plus P1 P naught C naught, and this will be G2 plus P2 G1 plus P2 P1 G naught plus P2 P1 P naught C naught. Then finally, this C out C4 is the last output. Okay. So, this is given by G3 plus P3 C3, this is equal to G3 plus P3 C3 is from the previous expression, G2 plus P2 G1 plus P2 P1 G naught plus P2 P1 P naught C naught. So, finally, we will get G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G naught plus P3 P2 P1 P naught C naught. So, we are going to generate all the carries. C naught is given as input carry, then we will generate C1, C2, C3, C4 using these Boolean expressions. This is the second step. So, what is the circuitry required for this one? So, this depends upon only C0, P's and G's. Okay, we have generated 4 P's, 4 G's and then C naught. Carry generation network. If you call as CGN. So, basically we have 9 inputs. Out of which this is C0 line, this entire line is vertical line is C naught, and this is G naught we have generated in step 1, G1, G2, G3 we have generated in step 1. Similarly, P naught, P1, P2, P3 we have generated in the step 1. Okay. So, what is the expression for C1? We have derived C1 as G naught plus C naught P naught. Okay. This was the expression we have derived, G naught plus P naught C naught. So, simply this requires C naught P naught AND gate, this dot represents a connection. This is C naught P naught, and then you have to AR with G naught. This is G naught so this will generate your C1. Similarly, what is the expression for C2 is G1 plus C1 P1, this is equal to, if you substitute this C1 here, G1 plus G naught P1 plus P1 P naught C naught. Okay. So, we can have this previous one is we have C1 P1. So, C naught P naught is there, this term is already there here. Okay. So, we can take that term. Okay. This term is nothing but P naught C naught, that I have to AND with P1 and with P1, so that this entire term is generated. Then G naught P1, this is G naught P1, second n term is generated, then G1. So, these three if you OR will get C2. Similarly, you can generate C3 and C4 using logic gates. So, here among all the paths, the path which takes the maximum computation time is the time taken to generate all the carries. Okay. C max if I call as, for example, if I take between these two, which one is the longest path? This is one OR gate followed by an OR gate, AND gate followed by OR gate. Okay. This is also another AND gate, another AND gate, another OR gate. So, this path is take more time. So, like that if you take the circuit diagram of C3, C4 also, so among all the paths, the maximum time taken by the signal to propagate from this C0, G's and P's to C1, C2, C3, C4, that computation time if we call as C max. So, this C max is the maximum computation time required to generate all the carries. So, in the first step what is the computation time is T XR, here also we will call as T max instead of T max, C max, T max. Okay. Or you can also call as otherwise, because you are calling as this as CGN, you can call as CGN. Now, we have generated all the carries. Okay. And the last step is, once if you know the carries, I will represent this entire circuitry in a block. Okay. This I will call as CGN. What are the inputs and outputs of CGN? Is we have 4 P's, 4 G's and 1 C0. C0, G0, G1, G2, G3, P0, P1, P2, P3, and what are the outputs are C1, C2, C3, C4. So, after the first step using this AND gate and exclusive OR gate, we have generated all P's and G's. Second step, using this carry generation network, we have generated C1, C2, C3, C4. Okay. So, what is the last step? We have to generate the final sum and final carry C4. C4 is the final carry, of course. So, what about S0, S1, S2, S3? As I have defined, S0 is A0 exclusive OR with B0 exclusive OR with C0. This is nothing but G0 exclusive OR with C0. So, this you can take from here itself. This if you are exclusive OR, this is exclusive OR, because A0 B0 is exclusive OR of G0. So, this is exclusive OR, this will give some bit S0. Similarly, S1 is G1 exclusive OR with C1. So, C1 is here. So, you exclusive OR this with this G1. This G1 is nothing but this G1. Okay. I have not shown the connection. This will give S1. Similarly, C2 if you exclusive OR with G2, you will get S2. C3 if you exclusive OR with G3, you will get S3, and this is C4 is the final carry output. Okay. So, this is like C4 is the final output. Some bits are S3, S2, S1, S0. Okay. So, here also you have generated this in 3 steps. So, you have generated S0, S1, S2, S3 and then C4 is the final output. And what is the third step generation of the third step is generation of all the sum bits. So, what is the time taken to generate all the sum bits? Only exclusive OR operation. So, this is another T XOR. So, the first step also will take T XOR time to generate all G's and P's. Second step will take T CGN. This CGN depends upon this Boolean expression that we have derived. This Boolean expression, to implement this Boolean expression, what is the maximum time taken? That will be T CGN, and to generate the last step, third step is T XOR. So, the total computation time of this CLA is two times T XOR. The first and third step requires the same time T XOR plus T CGN, the time taken to compute this carry generation network. Okay. So, this is fixed regardless of the number of bits. Okay. You can take 10 bit addition, you can take 20 bit addition, you can take 100 bit addition, this is same. Whereas, this slightly there will be increase in this T CGN if you increase the number of bits. Okay. So, in that way we can reduce this carry propagation time. As a result of that, this carry look ahead adder also can be called as a fast adder. Now, if we want to realize or if we want to model this carry look ahead adder using gate level modeling, it becomes very difficult because here we have lot many gates. Okay. But using this data flow modeling, we can easily write the Verilog code. Okay. Now, what is the Verilog code? Using data flow modeling. So, I will write module CLA 4 bit data flow. I will give the name as CLA underscore 4 bit DF. So, what are the total inputs and outputs? We have C4 final output and then we have 4 sum bits, sum S, then we have 4 A's, 4 B's, C0 is the input carry. Okay. This we have already used in the data flow modeling of look ahead carry also. Here also we have used this. Okay. This A's, B's are available as the inputs and C0 is available. Outputs are S3, S2, S1, S0 and final carry. Then you can define the values like output C4 is scalar. So, I am writing separately, you can combine with vector also, and other outputs are 3 to 0 S, because we have S0, S1, S2, S3. Similarly, input C0 is scalar and another vector inputs are, we have 3 is to 0 A comma B, both A and B are 4 bit numbers. And then we require some wires also. So, what are the wires required? You see here the first step is generation of G's and P's using this exclusive OR gates. Second step is using these Boolean expressions will generate all the carries. Third step is using exclusive OR gate will generate all sum bits. Okay. So, the first block here will be, the first block is something like this P and G generators. What are the inputs for P and G generators? We have two 4-bit numbers A0, A1, A2, A3, B0, B1, B2, B3, and then we have another C0 as another input. So, using this, what we are going to generate? We are going to generate all P's and G's, P0, P1, P2, P3, P3, G0, G1, G2, G3, G0, G1, G2, G3. Then this we are going to connect to carry generation network. So, this will generate all the carries C1, C2, C3, C4. Then we have final sum generation. So, this will be final outputs sum S0, S1, S2, S3 and final carry C4. So, these are overall inputs and these are overall outputs. In between we are using some variables, this we have to define as a wires, as you have discussed in the earlier classes also. These are not accessible. So, we have to define these as a wires. So, how many wires are required total? So, we require 4 for P's, 4 for G, 4 for carries. Okay. So, wire 3:0 P comma G, wire 4:1 C. This is P3 to P0, G3 to G0, C4 to C1. C0 is actually input carry. Okay. This is about the initialization. So, what are the different keywords required to generate the first step? This is step 1, step 2, step 3. This is step 1, step 2, step 3. So, for step 1, so what is there inside this circuitry? We know that these P's and G's will be generated using AND gates and exclusive OR gates. Okay. So, I will write assign. First, I will generate all P's. Okay. P0 is equal to, so what is the expression for P0? P0 is exclusive OR operations, G0 is AND operations. Here you can write, instead of this suffix 0, you can write P0 is equal to A0 exclusive OR B0 comma, I am going to use only single assign for all the P's. P1 is equal to A1, you can write in the bracket also, it is up to you, comma A1 exclusive OR B1 comma P2 is equal to A2 exclusive OR B2 comma P3 is equal to A3 exclusive OR B3. Then semicolon. So, P's are over. Similarly, you have to write assign G's. G0 is AND operation, A0 AND with B0 comma, I am going to use only single assign for this AND operation also. G1 is equal to A1 AND with B1 comma G2 is equal to A2 AND with B2 comma G3 is equal to A3 AND with B3 semicolon. So, second assign is for all G's. So, this will give the step 1, and in the step 2 we have to use carry generation circuit. Okay. Assign C1 is equal to, what is the expression for C1? C1 is G0 plus P0 C0. G0 plus is R operation is this, P0 and C0. Here also I can use single assign using commas. Similarly, you have to write C2 is equal to, basically you have to write this Boolean expression, then for C3 this Boolean expression, for C4 this Boolean expression. Okay. So, we have only AND operation, OR operations only. So, AND operation with this, OR operation with this. Okay. So, I am not writing C2. So, this is a Boolean expression. We have comma C3 is another Boolean expression, comma C4 is another Boolean expression using AND and OR gates semicolon. So, this is second step. And third step is to generate S0, S1, S2, S3, assign. This C4 is generated here, S0 is equal to, this is exclusive between P0 and C0, right. P0 exclusive within A0, comma single assign S1 is equal to P1 exclusive within with A1, S2 P2 exclusive with A2, comma S3 P3 exclusive with A3. Then this is end module. So, if you want to write this data flow modeling, we have a simple code, whereas if you want to use this gate level modeling, it becomes very difficult because we have lot of gates here. So, this is about the Verilog code using data flow modeling for a carry look ahead adder. Thank you.